So welcome then to session 7. We're going to, as I just said, begin with a bit of the theory. So we need to end what we started on regularization, and then we'll go into the practical. So we won't do it all, but we may leave the high dimensional stuff for the next one. Okay, so I said I would do a comparison between different regularization methodologies. So then we're gonna sort of give the title to this bit as OLS versus RICH versus PCA, and then we'll also see a bit of LASU. Yeah, so I sort of mentioned this in words, and actually I've uploaded the theory notes, so you may have already read this. So I go a bit quick then. Okay, so what we're going to do is to try to compare these methodologies, at least from, to begin with, we want to have some mathematics to be able to compare them. And basically the SVD is going to be very useful. So by the SVD of the design matrix, we have the following. So we have that the beta lambda, so the RICH estimator for the betas is going to be equal to the V matrix that we had times a diagonal matrix. So diagonal, and then we specify the diagonal entries. And I think there was a typo, by the way, in this, which I hope I corrected in the notes. So I said that we were going to assume that the columns of capital X were centered and they had variance 1. So it was pointed out by one of you, and I'm thankful when you guys point out typos, that I had written X, X transpose X equals to the identity. So that's not true. It's only the diagonals that coincide in that case. Yeah. So of course we're not assuming, we're not uncorrelating the columns. So that's pretty much what PCA is doing. But that's not what we start with. Yeah. Okay, so as in we only transform the design matrix to be centered and have unit variance for each of the columns. Okay, so diagonal matrix. So the RICH estimator can be written as, this diagonal matrix. Actually, let me keep the J for the PCA. So I, and then DII, so this is from the D matrix, okay, that's squared, plus lambda, and then times the U matrix transpose times the Y. And we also have that the OLS estimator is just the same guy, but when we plug in the value of 0 in the lambda, okay? And then what we have also is that, and this is the way of comparing things, is that the RICH prediction of the responses is going to be, so this is defined as simply the product, right? So of the design matrix times the estimator, and that's, that should be sort of familiar to everyone. And so what we have is that if you do this computation, then you'll find that this is just the sum. And again, maybe I wish to keep the J, yeah. So the sum from I equal 1 to P, so all of the elements, and here, crucially, we're going to get the square there, DII squared plus lambda, and we're going to have here the ith column of the U, okay, and then the dot product of these guys, yeah. So I will comment on this in a sec. So let me just write, and also the Y hat, which is, X times the beta hat. Then you'll see, and this just plugging in the value of lambda equal to 0, or actually just, you can compute it, and you'll see that it does coincide. And so this is going to be just this sum. As usual, do interrupt if you see any typos or if you have any questions. Okay, and then for PCA, we get that we're going to have this guy to be, so essentially here, rather than defining it through the parameter, what we have is precisely that the prediction is defined first, okay? So first, what we say, so maybe I wish to, okay, so let me mention then, let me comment on the previous sort of expressions. So, we have here the OLS prediction. So the OLS prediction, we sort of used to it. So it should be familiar to everyone that what you do is you project, you have this set of, this set of vectors that are uncorrelated, and you then go and do, okay, so and this set of vectors sort of spans the column space of the design matrix. And so what you do is you project your data onto each of these elements, and then sort of take it in that direction. Yeah. So it's really just the projection onto the subspace, of the columns space of capital X, but written in terms of the U's rather than the columns of X. Yeah. And what we see in rich is that we get exactly the same sort of expression, but what's going to happen is that, this term in here, so this fraction in here is going to be less or equal than 1. And we see that when lambda equals 0, then of course it's equal to 1. So we recover the OLS prediction. And instead, if lambda is very large, so if we penalize a lot, then this guy is going to be close to 0. So if it is close to 0, then what this is saying is, okay, so we're going to still project, but we're going to shrink on each direction. Yeah. And there are intermediate cases, right? And what are these intermediate cases? Well, let's take lambda to be, sort of some not too large and not too small values. So let's fix that. And then what we can play around now is with the D's, yeah? And we cannot play around with it, but let's imagine different values of D's. Well, if D is very large, then it will become dominant in the denominator. And then what we get is that this guy is close to 1. So what that means is that for the directions that have maximum variance or very large variance, we're not going to shrink the projection very much of the data. While for those that have very small variance, so for those that have, that don't really explain a lot of the design matrix, then we'll shrink them a lot. Yeah, basically with rich. Yeah. Okay. Okay. So then let's look at PCA. So in PCA, what we're going to do is we start by constructing the projection. And what are we going to do? Well, simply we're going to project. So we're going to project our data onto exactly the same set of guys. But we're going to do so up until the J. Yeah, so we defined the J earlier as, well, in the last lecture, yeah, as being the number, the minimum number of elements of PC or principal component elements that explain, a certain amount of variability in the design matrix. Okay, so what we've done is something intermediate, or something that is related to the previous, right? So we've, for the first J of them, we leave it as the OLS, and then for the rest of the principal component projections, then we're going to do extreme rich in some sense, yeah. And in fact, this can be seen as a limit of, this is in the notes, as a limit of regularized procedures, yeah, the PCA. Okay, so so sort of if we establish the this parallelism between rich and PCA, then so the sort of extreme case of rich in some sense would be this PCA. And so let's think, let's think of PCA to get intuition for rich. So this sounds like a great idea. You say, well, let me just keep those guys that explains most variability. And that sort of sounds good. But actually, what variability are we talking about? So I did say that this is the variability of the design matrix. So it could well be that the Y is not very well aligned with the column space of the design matrix, in which case this PCA, and by sort of extension, and I'm certainly, we have a bit of a leap of faith here, but it's actually true. We would need to prove it. By extension, rich will also suffer from the fact that if the Y is not very well aligned with the column space of the design matrix, then as in its variability is not with the variability of the capital X, then rich is not going to be very good, and the other way around. So if it is well aligned, then it is going to be good. So this is what the following theorem says. So theorem 3, we have that if we assume the Y is given by this linear model, so actually does follow the linear model, which is implicitly saying that we have this alignment in variability, then, well, and other assumptions, regularity, other regularity assumptions. Well, actually, let me just say assumptions, yeah. Assumptions, including lambda small, or lambda sufficiently small, then we get that if we look at the covariance of the OLS, okay, so this is the alpha hat, beta hat minus alpha beta, this product, and then times, so it's the product, sorry, of the previous and this guy. Okay, so this would be the usual covariance matrix. Let me now, so I wrote this too big. Okay, so let me now subtract the following quantities. This is now for rich, and this is now beta for rich as well, minus alpha beta. So note that okay, it's not going to fit. Okay, so let me just write this. I'm writing this bit here. Yeah. Okay, so it's the same quantity, and I'm transposing it. So that should be sort of, well, it is in the notes. So, so note that this guy here is not exactly the covariance, yeah, because for the covariance we would need to subtract, rather than this guy, we would need to subtract the expectation. And remember, this is, rich is biased, so the expectation is not equal to the true parameter, although asymptotically it should be. So if we subtract, if we take the difference of these two guys, then this is going to be positive definite. Okay, and that's to say, this is sort of saying that the first element is larger than the second element in a multidimensional sort of sense. Yeah. Okay. So, so you've seen why I'm writing in capital letters, because my writing is terrible. Okay, so okay, so that's what this is saying, yeah? So what this is saying is that if lambda is sufficiently small, then we're going to have this sort of dominance of the OLS over the rich, or maybe dominance in terms of, dominance in this way. And this is, by the way, going to imply, so remark, theorem 3 actually implies that the prediction error of rich is smaller than that of OLS if lambda small enough. Yeah. which means, of course, that we have regularized a bit and we have introduced we have traded some bias with some variance. Yeah? Okay, and then last, I commented on this. So regarding lasso, there is something pretty cool about it, and is that if we assume the linear model again, okay, and also that beta can be decomposed as, comprising two different betas here, with beta naught being in some, having p naught dimensions, where p naught is going to be between 1 and the original p, which is the size or dimension of this beta, then and let me say, of course, the beta one is exactly 0, okay, but 0, of course, from this p minus p naught, in that space, then again, if we have that lambda is small enough, the prediction error of lasso is going to be approximately the prediction error of the oracle estimator. And the oracle estimator is that which knows these assumptions. So it knows that we're assuming that the linear model is true, and that there are only p naught non-zero coefficients together with the actual value of the p naught. Yeah. So that which knows these assumptions and the value of p naught. Okay, so it can exploit these things. So it turns out that lasso, even not knowing these things, it will select. Well, it will have prediction error that is comparable to this. And in fact, and this is, I'm jumping ahead a bit. Indeed, it will, it does this. It gets this really good prediction error because. So it's in addition to this. It does correct model selection. Yeah, performs correct, and not only automatic. So in the last session, I said automatic, which is true, but it's more than that. So it's correct model selection. Yeah. Okay, so we stop here. We stop here and go into the practical, so we don't. Okay, so it's a bit late. Let me then stop sharing and now share the screen. So I want to have it. Let me just do it the right way around. Right, so you should be seeing this now. Okay, so we left it in Excuse me. So we had some, yeah, so we left it here in model selection. So do we have any questions? Are there any questions about this very last bit of the second practical, in which basically what we're doing is, generating some data that comes from a polynomial model. So this is, so this is a linear model, but it's, remember the linearity is defined through the dependence on the betas and not really on the design matrix. So the design matrix can contain, columns that are just the powers of some columns. That's fine. So yeah, so we generate this sort of polynomial data in some sense, and then we just try to select, the best model with cross validation, and we use as a criterion AIC, BIC, and cross validation. Yeah. Sorry, I'm let me just rephrase that. So we use a selection method, AIC, BIC, and cross validation. Excuse me. Okay. So I guess if no one's asking, then everything is clear here. Yeah, and then we get this plot that tells us that BIC is more strongly, so the three of them select the correct degree in the polynomial, and BIC does so more sort of aggressively. And this is because there is an actual model within those that are being considered, right? And then the other comment is that AIC and cross-validation seem to give very, very similar lines, and that's to be expected from the theoretical results. Although, of course, this is a finite sample experiment, and it could well be that the lines don't match as well as here. Yeah. Okay, so if there are no questions, we go to practical 3. So again, I think we'll leave the last bit of the practical 3, so the high dimensional example, for the next practical. And so let's focus on this cancer data. And essentially what the practical revolves around is really this GLMNet package that is going to be performing ridge lasso, or so-called elastic net, which is a linear combination of the two, so that you get the best of both worlds. And so then it's really just about sort of, so I can comment on some things here, but does anyone have any questions about this bit? So yeah, I think the way we'll do it generally is that I let you ask questions first, and then otherwise I go through it.
Why do we set the parameter family to be equal to Gaussian?
Why do we set that? Because so that's generally determined by the response variable, right? And the response variable here is this LPSA. I seem to remember. I can't find it. But if you okay, so this is the LPSA, and so I didn't mention it in words what it is, but if you look at the structure of prostate, then you find it here as the penultimate value, or you could have just looked at that one. PSA. And then you see that it's got negative values, positive values, because it turns out to be the logarithm. So I don't know whether I mentioned this here, but it's just the logarithm of some value, and this is clearly continuous random variable, with negative and positive values. So it makes sense to model it, at least in the first instance, as a normal distribution, right?
Okay, thanks.
Sure.
I've got a question, which is, am I right in thinking that the fraction of deviance explained will always increase if you reduce lambda?
So that's a good question. That's a general, yes, that's a general, I guess, intuition. And in this case, it is more so because we have, a common setting in which the number of covariates is less than the number of data points. And so essentially what's going to happen is that in this case, it's clear, right? Because the deviance. So remember what Rich is doing. Rich is taking this sum of of the the data fidelity term and the regularization term, and if you are in this linear model, so with a Gaussian family, then it doesn't matter whether you're taking the negative log likelihood or the deviance, that both will be the sum of the residuals, the square of the residuals, for the data fidelity term. And so if you are minimizing the sum of this guy together with another guy and then rule out this second guy, so take lambda to be very, very small, then you're minimizing the deviance.
Yes.
So yes. So in this case,
okay.
in this case, it's very clear, right? In other cases, it's it requires a bit more thought, but yes, as a general rule, that is true.
And also, sort of similarly, in general, would you expect? So, sort of intuitively, it seems like you might expect that if n is bigger than p, your fraction of deviance explained would sort of increase up to something less than 1. And if n is or if p is a lot bigger than n, you'd expect the fraction of deviance explained to increase up to 1, roughly. Is that what you'd expect?
Yeah. So for that, you need to define what the denominator in the fraction is. Firstly, right?
Okay. Yeah.
So
I guess it's a saturated model with
exactly. So you need such kind of assumption. So this is, so let's see, what do we, even in the high dimensional, right? So in the, so this works for this case of p less or equal than n, yeah, because you can compute the deviance, the full deviance, just being, the deviance corresponding to all of the parameters that you're considering. So it makes sense in this setting, but it doesn't in the high dimensional setting. So there is, so actually, even though I included this, I actually like the second the second option of the plot. So what is called the regularization path. I like it a bit more than this one, for that reason. So if you change here deviance as the x variable to be lambda, then you'll get this regularization plot. Sorry, let me actually make this as small as possible. And then you get this plot in which the deviance doesn't play any role.
I suppose you could look at the deviance versus log lambda.
You could do.
I don't know if that means anything really, but
yeah, exactly. I mean, it would have the same issue of if you're looking at the fraction of the deviance. But if you, so you're saying to look at the total deviance versus log lambda? I mean, you could do that, but I guess these plots, what they wish to show is really, how the parameters are going to behave, depending on, how aggressive you are with the regularization or how much deviance you want to explain. And so if you do, deviance versus lambda, then you lose the parameters, right? But I mean, it depends on what kind of question you're trying to answer. So it may well be that you're not satisfied with these two outputs of your fit. So I mean, these are just some very standard ones, basically, that I used. More questions?
Got another one, which is when you change lambda, you see that one of those parameters sort of moves either side of 0. Is that something that usually happens or like rarely happens? So the very bottom one at the start.
Yeah, that's a very good question, because it's rather strange, at least at first thought, that you have certain intuition, because of course this sixth variable, when you have no regularization at all, then it turns out that it has the meaning that if you add a unit of it, then the response will decrease. While if you go, towards this amount of regularization, then you have the opposite meaning. This is generally a result of correlations. And what is very important here is to say, well, in this case, clearly we killed these two parameters. Two of them. So I can't distinguish between these two, which one is which, but 8, for instance. So you should be interpreting, the model here and the model here in a different way. You should be interpreting here, the model. If you're looking at interpreting the coefficient for the sixth variable, then here you should be interpreting it as controlling for the other 7 variables. Then the meaning is that if I add a unit of this one, then there will be a decrease of 0.2 in the response. And then the interpretation in this other model is, well, controlling for, so having killed 2 variables and controlling for the other 5 variables, then my interpretation is that as I add 1 unit of this one, then I will have an increase of, say, 0.05 of the response. And I mean, what that is saying essentially is that so it's the same discussion that I had at the very beginning in the first practical, saying, that there is quite a difference between the interpretation of a coefficient when you include other variables and when you don't, right? Because when you do, then you're sort of isolating a bit better the influence of that parameter on the response. While when you don't include others, and in this case, you're not including 2 of these, then you're sort of embedding into the rest of you're embedding into the remaining parameters, the sort of crossed influences. And
so would this sort of weird behavior where it starts out below 0 and then goes above 0 suggest that, like, from this data you can't separate out the effects of that individual parameter? You have to take into account the sort of interaction with others?
Well, I mean, there would always be some sort of interaction, right? I mean, there's never correlation equal to zero. I mean, hardly ever correlation equal to zero. Sort of what is called an orthogonal design. So orthogonal design can happen, but generally that's when you're able to design the covariates. So when you have control over them, so you design the experiment rather than it being a more observational study. And the observational studies, generally you don't have this orthogonality. And this I mean, no, I mean, you can control for the others. It's just a matter of whether you include them or not. So if you do include them, then you control for them, and if you don't, then it is embedded. Their influence is, because the correlation is not going to be zero, because this is the case for this example. Then it's going to be embedded into the rest of the parameters. But it's just that's certainly an important observation that you can draw from this regularization path. It's precisely that if you choose a regularization that is on that sort of beyond this -1 for the log lambda, then probably you've killed the two parameters, and then you need to reinterpret things. You need to be aware of that change in interpretation. I don't know if that answers the question.
Yeah, no, that does. Thank you.
Yeah.
Also, just why are there lots of 8s at the top?
Lots of 8s. I don't know.
Okay, fair enough. I also had lots of 8s when I did it.
Yeah, I would need to look at the documentation to know what that is doing. Yeah, off the top of my head, I don't know. I don't think
numbers. Incidentally, the numbers change when you do it with the lasso.
Yeah, so exactly. So I'm just thinking now. So that is, yes. So I think that is probably the number of active parameters at each of the values. So in rich, we're never going to kill exactly the the coefficients. So they're always going to be just very, very small. If anything, remember what I said at the beginning of this lecture. That we have this ratio of the d's over the d plus lambda. So even if lambda is very large, that ratio will never be exactly 0.
I found it in the lasso plot now, so yeah, that makes sense. Thanks.
Right. So I presume, yeah, exactly. So I presume in lasso you do have a change of those values because they are exactly killed because of this plot that I was, this graph that I was including in the last theory lecture that was saying that we have this diamond. And so because of this diamond rather than the circle, you will always, you will sometimes, and actually in most cases, when you go to higher dimensions than just 2, which is the plot that I was, or the graph that I was showing, then you will exactly hit the corners of these diamonds and you will kill, when you have, of course, lambda large enough, you will kill some coefficients. So let's see, where is lasso here? That's rich. Have I not? Should be somewhere. Okay. Well, it is here. Yeah. Okay, just make this larger. And then here, lambda. Yeah. So here we get the lasso plot. And then, yeah. So then it tells us that. So we see that here, one of them was killed at the very beginning. So we get 7 of them. And then as we kill them, it tells us, yeah, which are being killed. How many are left, basically, being active in the fit. Okay, more questions?
Regarding the graph in the cross-validation section,
yeah,
there are those 2 dotted lines, the left one being the minimum value of lambda. That's optimal lambda. Yeah.
Are you talking about this one that I'm showing now?
Yeah, exactly.
Okay, yeah.
So the leftmost line being the smallest, the lambda value that gives the smallest cross-validation error. And then you mentioned the second line being one standard deviation above that.
Yeah.
So you can't just to like hedge against overfitting. So would you be able to give a bit more intuition as to why you would do the second one, or like which one would we pick if we were doing it?
So okay, so I mean, so this is a bit of an art. Let me say that first, because generally speaking, the results that would give you some guidance as to what to do are asymptotic. And so, with finite samples and depending on the distribution, many other things, you're a bit left, by yourself to decide these things. But what is clear is that cross-validation, because after all, I mean, so with cross-validation, what you're attempting to do is to have this estimate of the prediction error, right? I mean, that's how you construct it. You construct it so that you have some sort of empirical analogy of this prediction error, and so you try to minimize that. Yeah. But because you are using the same data again and again, even though you are removing part of the issues that you would have, in training versus testing, cross-validation will still give you some bias. It will include some bias in itself. And so the lambda that you get from cross-validation will not be the absolute optimal lambda if you knew the distribution and were able to really compute the prediction error exactly. Yeah. So then that's a long way of explaining what I want to explain, but what I want to say is that the lambda you select is not really for finite values, and in many examples, it's just not the best value. So then you go and use the usual intuition from physics, and you say, well, let me add, let me try to look for some sort of, the lambda has a variability, right? In that if you change the data, then the lambda will vary. And so let me just try to have some idea of how much it varies, and then you have, this standard error, and then you add it, and you have, a bracket of values in which you sort of guess that it would be, a better estimate would be contained. A better estimate of the value of lambda that would minimize the test error when you have the actual distribution rather than the estimate that comes from cross-validation. Yeah. So then you could say, well, then what do I do with that bracket of values? Something that you could do is just to take the average, for instance, of the estimate. I mean, there is just not a correct answer, to be honest. But I guess what this is showing is that you shouldn't be trusting 100% the minimum value of lambda, and that you really have a portion of values or a range of values that you should be sort of considering as possible better values for lambda. And indeed, if you look at the graph here and look at the test error, then you'll see that so this 1SE. So this is, I wrote LSE by mistake, so it's 1SE. Yeah. So it's now corrected. 0. So we look at 0. So it's something very close to 0. So if we go here and we go very close to 0, then we see that it contains the minimum of this test error. Again, this test error is not really the true test error if you need the actual distribution. Yeah. So it's now with a different set of data. So had you chosen a different set of test data, then the minimum may fallen around here, or if that set of data was very close or very similar to the data that you used to train, and it may have fallen on the right as well. So I guess what I wanted to say there is you should be considering things that are a bit beyond this value. And in this case, we see that it coincides that it's between those. And actually, if you take the average of the two and then take the logarithm, then that's going to be pushed to the right. So it's going to be closer to this other value, and that would have been a better estimate. But that's only an observation that you can make after seeing the test data, which you shouldn't see when you're training things. So I guess I gave you a very long answer to say there is no right answer. But I would probably, so firstly, what this shows is be cautious, don't trust, the procedures and procedures, blindly. And second, maybe there is a better way of doing it, which is actually considering that 1C and the first estimation and taking something in between that. But again, this is not rocket science. Don't know if that answers.
Yeah, no, that makes a lot of sense. Thank you. Is that one standard deviation out of all the lambdas you try?
Yeah. So so I refer you to the documentation as to how that is computed. If you really want me to give you a good answer, then I can take a look as well. But it's not an immediate calculation. It's not a very straightforward calculation. I mean,
is it a general fact that it will underestimate the lambda by cross validation underestimates? Is that kind of the lower bracket of the region or not?
It doesn't need to be. It doesn't need to be.
Is the standard error like above and below the one the cross validation one gives you? Because you were speaking as if the cross validation one was the lower bracket.
Yeah. So exactly. So that's a bit what you could think. Yeah. So you could be thinking that there is yet another value on the left. Yes. But so
right. Okay.
So let me just think for a sec. So generally you will underestimate, I think you will underestimate because, excuse me?
The code only returns, it's not like it returns an error, right? It returns another estimate of lambda. It doesn't seem to say it's like a standard error or something like above and below. It just seems to give you another point estimate. Yeah.
So I mean, so it will underestimate because this bias will tend to be negative because cross validation uses, this splitting will be using always the same data, the training data. And so it will be overconfident in terms of how little regularization you have to do. So generally speaking, you if you want to, so let me put it in a different way, a more intuitive way. If you wish to predict, and you are using sort of similar data to test the prediction and to train the model that you're going to predict with, then that will be an easier job than if you wish to predict something that you haven't seen the data for. And so in that case, you need a bit more regularization to be able to generalize a bit better. Intuitively, that's what's going on, basically.
Thank you.